So today's lesson's on the integrated rate law. And again, if you are in calculus right now or some type of calculus, it's helpful, although you don't have to be in calculus to be able to understand what we're talking about today, but it does help a little bit. We're not actually going to do calculus. The calculus has already been done. There's been some equations that have been converted into a different form using methods from calculus, particularly something called integration. And so it helps if you understand what that is, but it's not required. So today going forward, we're going to be looking at simple decomposition reactions where you have one single reactant. So something like A breaking down into some other things. We can just call it B, for instance. Okay, and so A is either going to be a gas or something aqueous whose concentration can change. Okay, and so if A is a first order reactant, the differential rate law, the ones we've been talking about so far, would be written as rate equals Ka to the first power. Okay, and again, that's not because necessarily there's a 1 coefficient here. It's by experiment using something like the method of initial rates. So if A is a first order reactant, this is how we could write the differential rate law. Now, in calculus, we can describe the instantaneous rate as the instantaneous change in concentration of A divided by an instantaneous change in time. And since this is a reactant whose concentration is dropping, and so that would be like a negative rate, and in chemical kinetics we always talk about positive rates rather than negative rates, we put a negative sign out here. So for a first order reaction, the rate is written out this way. And we would say that is equal to Ka. Okay, so I've already gotten that written out for you right here. This is just another way of stating the differential rate law. But we've actually, instead of using the word rate, we've said what the rate is, mathematically speaking. Okay, so this just means rate equals Ka to the first power. Okay, now, in calculus, you can do something called integration, which is kind of like moving up a level. If you're not in calculus, a great comparison is if you're talking about speed and acceleration. Okay, so let's say you're accelerating really continuously. You're going faster and faster and faster. Well, the speed itself would be changing. But if you could measure your acceleration really well, you could also figure out the speed at which you're traveling at any moment in time. So acceleration and speed and the actual distance you've traveled, they're all connected. It's just kind of like a different level of analysis. And so in calculus, integration can take us from one level to sort of a more basic level, okay? And when we integrate this equation, we have to do something called integration by parts if you're in calculus. Integration by parts. And again, if you're interested, we basically put all of the same variable on one side of the equation and all the other of the other type of variable on the other side of the equation, where we basically put 1 over Ka on the same side as this dA, and there's a negative in there as well. I think we end up moving the negative to the other side, but then we put the dt, negative dt, all by itself on the other side of the equation. So we've kind of rearranged this equation, and then integration by parts can lead us to this form of the equation. Okay, so if you're not in calculus, you kind of just have to trust that the information here in the one I've got circled in red, it's got the same information essentially that we have here in the equation in blue. It's just a restatement on a different level of analysis. It's the integral rather than the derivative, okay? And so this equation here has the same form as the equation of a line. Remember, in standard form, a line is y equals mx plus b. And this is basically, you've got two constants and two variables in this equation. Your variable is y, and that's your dependent variable. Your independent variable is x. So those are your variables, right? Those are your variables. And there's also a couple constants in there. The m and the b, these are constants. And that's exactly the type of thing we have going on over here. There is k, the rate constant. And that kind of corresponds to the m in this standard form of a line. And ln a0. Let me tell you about what that means. This is the natural logarithm function, the natural logarithm of a0, which is the initial concentration. And so in calculus, you kind of have to define like your final and initial states a lot of the time when you're doing like a definite integral. But a0, a sub 0, just tells us the initial concentration, and that's a well-defined specific number. So the natural logarithm of a well-defined specific concentration would also be a well-defined number. It's a constant. It's not going to be changing. In other words, once you start your reaction, you had the initial concentration that you had of whatever A is. Its initial concentration got locked in from the start, and the natural logarithm of that concentration would also be locked in. So that's a constant. Okay, time is our independent variable, which is like the x over here. So there's our variable, and the other variable, the dependent variable, is the natural logarithm of the concentration of A. So as A is changing throughout the course of the reaction, the natural logarithm of A is also going to be changing. Okay, so at the end of the day, we've got two constants, the rate constant K and the natural logarithm of the initial concentration, and we have two variables. Time, as the reaction progresses, time is changing, and the concentration of A, along with the natural logarithm of the concentration of A, is changing. Okay, so this is a line. So what's the main takeaway from this integration? Well, if you have a first order reaction, if the rate is K times A to the first power, when you graph the natural logarithm of A, concentration, versus time, you will get a line. And the line produced has a slope of negative K. Okay? So if you have a first order reaction, and then you take your data and you take the logarithm of your concentration data and you graph it versus time, you're going to get a line. And the line has the slope of the negative of the rate constant. Okay, that negative value basically comes about because when we defined the rate for a reactant, we put that little negative sign in there, and that negative sign has basically stuck around during the integration. But the rate constant K is hiding in here, okay? So, let's see. You know what I did on my integration by parts? The K should have been over here with the dt. If you're an expert in calculus, you might have noticed that I did that. So we keep negative K, and we integrate negative K with respect to time. And that gives you negative KT. anyway. But so this is the equation of a line, and so there is a connection between a first order reaction and its differential rate law and this thing called the integrated rate law. Let's have a look at a second order reactant. Okay, so here we've got the differential rate law, which tells us that the rate of reaction with respect to A is proportional to A squared at every moment. So the concentration of A squared times some rate constant gives us the actual rate. Okay, so this might be just a different reaction, A decomposing, a different A decomposing into some other stuff, some other reaction. If it's actually a second order reaction, when we integrate it, it gives us a different equation, but we still have the same type of thing happening. We've got two variables, which I was supposed to highlight in yellow, I think. The variables are yellow, right? This is like our y, and t is our x, and we've got two constants, the rate constant, and instead of logarithms, it's inverses, but the inverse, or reciprocal rather, the reciprocal of our initial concentration is going to be the y-intercept in this equation. So again, y equals mx plus b, and so just like we have two variables in the standard form and two constants, same type of thing. So this follows the form of a line. This is the equation of a line. And so if you have a second order equation, if your reaction actually is second order, and you graph this stuff, you'll get a line. So when you graph the reciprocal of concentration versus time, then you get a line. And the line has a slope of k, positive k this time. Okay? And so whether it's first order or second order, there are ways to graph the data which will generate a line. And here it's with the natural logarithm of A versus time. And this is the reciprocal of A versus time. Okay, we'll see some examples about how this works in just a moment, so it probably sounds a bit abstract for the moment. But at the end of the day, something that you should take away from today's lesson definitely is you can graph the data to get lines. Now, let me show you kind of the general idea about all of this. Okay, so if you have some reaction and you're looking at the concentration of A over time, and let's say that the rate is a first order type of rate law, the data might look something like this. Okay? However, if you go and instead of graphing the actual concentration, if you instead graph the natural logarithm of A along the y-axis versus time, interestingly, you get a line. That same data will get converted into a line, and it's going to have a downward slope, and if you can find the slope of this line, the slope of that line will be the negative rate constant, okay? Or the negative of the rate constant value. So that same k will show up in the slope, okay? Now, if your reaction, that's for a first order, right? If your reaction is a second order, again, rate for a second order reaction with one reactant is something like that. You know, it's kind of hard to tell if you just simply look at the graph. It might look kind of similar, although careful inspection, you'll see that this curve is a little bit different type of curve than this one, but they're both curves, like downward sloping curves. Right, where you're getting less and less of the stuff over time. But this curve is actually a different type of curve. And if you instead use your data and instead you graph the reciprocal of concentration over time, you will get a line going upward, and the slope of this line is actually the rate constant K. Okay? That same K from the differential rate law will show up in this graph. Now let me say something here. If you take a first order reaction and you graph the natural logarithm, you get the line. Natural logarithm versus time, you get this line. If you instead tried to graph the reciprocal, I don't know what the graph would look like. I don't know that off the top of my head. But if you graph the reciprocal of concentration, in this case, for a first order case, I don't know what the graph will be, but it's not a line. Okay? It's not a line. That's only for second order. And if you take a second order reaction and you try to graph the logarithm of A versus time, you won't get a line either. The only time you get a line is if you've done the appropriate integration in calculus for a first order or a second order reaction. So this actually allows us to determine, is a reaction first order or second order? If you look at a graph like this and you see that it's a line, the fact that it's got natural logarithm versus time and it's linear tells us it must be first order. It must be first order. And that kind of lets you go backwards to recognize the differential rate law. If you see a graph like this, it will tell you it must be second order, which allows you to, again, kind of go back and establish the differential rate law. Okay, so back to the packet here. I want to talk about zero order. Zero orders are actually kind of funny because they have a constant rate. Okay, so here, if you think about it, this would be something like, rate is K, A raised to the 0 power. And that's just K times 1, because anything raised to the 0 power, even if this thing is changing, when you raise it to the 0 power, it's just 1. And so K times 1 is just K, which means the rate is K. The rate is constant. Okay, that's what I wrote right here. If you have a constant rate, if you think about it, what would a graph of a reaction look like if it's got a constant rate? Okay, that's what a first order reaction looks like. A second order reaction, you have these downward curves, but what would a zeroth order reaction look like? Constant rate. For a constant rate reaction, what that would look like if you graphed the concentration of A versus time, it would be decreasing at a constant rate. which already is a line. All right, so the rate is not changing, constant rate. And so the slope of this line is k. And now technically, since it's decreasing, it's negative k, okay? But all we have to do is graph a versus time, and we've already got a linear graph. If you see something like this, it has to be zero order. It must be zeroth order. Okay? Has to be. So that allows you to infer the differential rate law. Rate is k, or ka raised to the 0, which is just k. Okay? So let's fill in the blanks here. It turns out you can also do integration by parts on this thing using calculus. And what do we see? We see an equation with two variables and two constants, just like before. But what are we graphing here? On the y-axis is concentration of A. On the x-axis, time. So A versus time. And that gives us a line with slope negative k, and the y-intercept is the initial concentration. That makes really, really good sense if you think about it. This y equals mx plus b thing. All right, remember this is called the y-intercept, and that's the slope. So where's the y-intercept here? Right there. And what are we graphing on the y-axis? Concentration. So that point right there, we call it A sub 0, and that is the initial concentration. The concentration at what time? Time equals 0. Okay, so the concentration at time equals 0. That's what that little subscript means. Okay, so we already have a line when we graph a zeroth order reaction, just A versus time. Okay, so graphing the concentration itself versus time gives you a straight line with a slope of negative k. All right, so disclaimer, Mr. Wilson doesn't like it when I say straight line. He says, Mr. Kaywood, all lines are straight. That's what makes them lines. So you don't want to confuse students and make them think that a curve is a line because a line is straight. It's like, okay, in a lot of AP chemistry textbooks, they call it a straight line. And so, you know, I will probably start saying line when they change all of the AP chemistry textbooks. But I do try to give Mr. Wilson credit for pointing out that all lines, if they really are lines, are straight lines. Okay. Anyway. All right, so finish up today's lesson. How can we determine the order of a reactant when we look at the data of A and time? By plugging in our data into each of the above equations, we see which produces a straight line. Which of them produce a line? That then will tell us the order of the reactant. Okay, so example problem, very quickly, and then we're done. We'll talk about half-life in a different video. Here's some data, and we're going to verify that it's a first-order reaction. We'll come back to determine the, well, we can do the rate constant as well, and we might as well answer everything on here. Okay, so here's our data, and I'm going to use Microsoft Excel to graph this data. I should have already typed it in, so I'm a little bit behind. Do I even have Excel on here? No. Let's see. I could probably use my Inspire calculator, but I'm just not even sure how to do that. So let me open this up and I'll just create a new sheet. We'll use Google Sheets. And yeah, I'll share it with you guys. It'll be in that same folder. And I'll call this N2O5 decomposition, because that's the reaction we're looking at here. N2O5. It says 2 N2O5s, and we're basically trying to determine or verify that it's actually a first order reaction. We're going to verify that this right here would be the rate law, the differential rate law. Now, if that's the differential rate law and we're trying to verify that, there is a way we can graph this data so that it'll be linear. So let me go ahead and type in this data, minimize that a little bit, shrink it down so I can type it in a bit more quickly. Oh, good, it's scooting over. That's great. Boom. So there's the data. I'm going to type that data in right here into this spreadsheet. Okay, so up here is time in seconds. And if you want to follow along in your calculator or also on Excel, I think that would be a great idea. And this is going to be concentration of N2O5 through the course of the reaction. That's measured in molarity. Brackets indicate molarity. Okay, so straighten that up. Boom, boom. Make them bold. All right, and I wonder if it'll let me zoom in as well. Like, do one of those. Cool. All right, so we've got 0, 50, basically, no, not every 50 seconds, every so often we measure the concentration up to 400 seconds. So this is the initial moment, the initial time, and what's the initial concentration? 0.1, 0, 0, 0. I can change the number of sig figs in just a second. 0.0707, 0.05, 0.025, 0.0125, and 0.0062. Oh, enter. Okay, now here's my data. Sure, let's make it look nice and center up everything. Now we've got it all typed in. I don't know if that looks nicer. Pop. Okay, and in terms of significant figures, looks like we're measuring the seconds to there probably is a way to set up the significant figures, but it's not so important for this illustration. But you could format the cells to show 4 decimal places here and 0 decimal places there. But this is the numbers. So let's go ahead and graph them. So I'm going to insert a chart. And the chart that I want, is it going to come up? Where's my chart? Okay. And I want it to be a scatter plot. There we go. Okay, so there's my chart. Okay, now notice that's not a line. Okay, that's a downward sloping curve. And that's what normally happens in a lot of chemical reactions, right? You get less and less and less and less of your reactant, and it's kind of slowing down. Now what we're going to do, this basically shows us it's not zeroth order. Okay, the data right here, if the data were already linear, we would have a zeroth order reaction, okay? But it's not already linear, so we know that the order of our reactant is not 0. Okay, it's not 0. So that's what this graph tells us. It's not 0. So it's probably first or second order. Those are the most common. So what we want to do is try 2 different transformations. Right here, I'm going to do the natural logarithm of everything, all those concentrations right there. So the natural logarithm of into O5 concentration. And in Excel, this is easy to do. I can just say equals natural logarithm of, and I can click the cell that I want it to do that for. Boom. So it's taken the natural logarithm. And if I click and I drag down, it will find the natural logarithms of each one of those to the left. Okay, so it just did a bunch of calculations for me. So I've got the natural logarithms of my concentrations now. Okay, and I can also do the same thing with the reciprocals, which I'll need in a moment. That'll be 1 over A. Okay, and so I can get Excel to do the work for me. 1 divided by the concentrations. And, right, so 1 divided by 0.1 is 10. 1 divided by 0.05 is 20. It's taken the reciprocals of my concentration. So now I'm going to make 2 other graphs and see what I get. I'm going to graph this on the x-axis and this stuff on the y-axis. And insert chart. And I don't know where my chart is. Where's my chart? Okay, so it gave me a weird looking graph. I don't want a bar graph. I want a scatter plot. Boom. Okay, now this graph here, I don't know why it took so long for that to show up. I'm going to zoom back in again. This graph here looks quite linear, although it's kind of an illusion. It's like, is it really linear? You can click on that, and there's got to be a way to format this thing and put a line of best fit. Chart style. Axis, data range. Let me see. I hardly ever use Google Docs in this way. I've got my scatter plot. Can I customize it? Goodness, there's gotta be a line of best fit. Or trend line is what they're called. Goodness. Anyway, I'll have to research how to do trend line on here, but you could confirm that this is linear. All right, I'm just not used to doing it except in Excel. So we've got a line. That confirms that this is a first order reaction. There's something linear hiding in here, but it's the natural logarithm of our concentration versus time. Okay, so that right there confirms that it is a first order reaction. Why? Because when you have a first order reaction and you graph the natural logarithm of A versus time, you get a line. And the line has a very specific slope. It's the negative rate constant. Okay, so in a later video, we could confirm that this is a line, and if we could find the line of best fit with its slope, the slope would be negative k, the rate constant. Okay, so we've just confirmed that it's first order. Let's do one more graph to show that it's not second order. It can't be both first and second order. It's one or the other. Let's graph this, insert chart, and who knows what's going to, okay, did that again. Scatter plot. Okay, and we get a curve on that, okay? So once I zoom out and rearrange all this stuff where I want, boom. All right, so concentration itself versus time is a downward curve. The reciprocal of concentration versus time is an upward curve. The natural logarithm of concentration versus time is a line, and the slope of this line would be negative k, negative rate constant.